Hello, we are Luca and Zurab, and today we are discussing paper parameterizable FPGA implementation of SHA-256 using blockchain concept. This paper concentrates on the design of parameterizable implementation of SHA-256 algorithm in FPGA imparting blockchain concepts. SHA-256 is the key principle utilized in blockchain architecture to impart security. Main goal is to introduce this new technology into VLSI domain for securing hardware digital system designs and SoCs, that is the systems on chip.
Let's talk about blockchain. Blockchain, as the name specifies, are a chain of blocks that represent open and decentralized digital database among transaction entities or persons who are verifiable and mutable. All the transactions are transparent to everyone within the network. Thus, it avoids the need of a third party, to verify the transactions done among the trading parties. Hash functions and digital signatures are two basic crypto primitives behind blockchain technology. In this technology, data inside the blocks are secured cryptographically using complex algorithm called SHA-256. This paper focuses on the design of parameterizable implementation of SHA on FPGA. Any bit length message on or transaction could be padded and converted to a 512-bit message to compute 256-bit hard hash digest. The architecture were simulated in the model sim and synthesized in Xilinx Vivado design suite using RTX 7 FPGA.
Blockchain can be explained in a simple way as a chain of blocks where information is stored systematically, and every block is interconnected to the previous block through its hash value. Its internal structure has two components, block header and transactions. Every block is indexed with a unique number known as block ID, created cryptographically. Connection between the blocks is established by storing the hash of previous blocks in the header of the immediate next. This structural form gives it the name blockchain. Block header is composed of 5 fields: previous block hash, nonce, block version, timestamp, and Merkle root tree hash. Transactions are the information that needs to be exchanged for value. Once the specific node called miner creates the new block after computing the appropriate hash, the transaction within it is communicated to the other nodes in the network.
A little bit about hash functions. Now, hash functions involve a set of complex mathematical operations and computations that convert a random length input message into a fixed length of output called digest. The hash function has some traits which we'll discuss now. For example, it is impossible to reverse engineer. A single bit input can change of single bit in input can completely change output. It also has ability to compress any length input into a fixed size output, and it has computational feasibility to find the same hash for two different input messages. Now let's move on to SHA algorithm. SHA-256 algorithm is composed of two function modules called message block schedule and compression function. In message schedule, the n bit message input is added with 1 bit followed by 0 bits until the following equation shown in the slides is satisfied, where k indicates the number of 0 bits to be added. Value n is then converted to its 64-bit binary representation and further added to the 448-bit intermediate value to get 512-bit message block. Now, this form block is hash of the previous one. Now let's talk about the compression function, which involves 8 registers called from A to H, also 6 logical functions, and another set of 8 registers from H0 to H7. We store 32-bit hash values, updated m times if there are m 52-bit message blocks.
Following functions are computed on each round and the registers are updated using majority function of first 3, choose function of the next 3, and sum and sigma functions of the rest. But after 64 rounds of operation, registers H1 through H7 are updated for I. ranging from 1 to m as follows. Final 256-bit hash value is obtained by concentrating 32-bit values H to M, HM to HM. The proposed architecture is designed in such a way that it could generate the hash for any n-bit message input after dividing the message into blocks of 512 bits each and performs the compression function and registers allocation iteratively. The architecture proposed was designed in Verilog HDL and simulated using the Model Sim RTL simulator. Billings Vivado 18.2 design suite was the software tool used for logic synthesis in FPGA.
We have several tables which represents the measurements taken. We have tables that presents the performance parameter summary for the design, and the second table that shows performance comparison among several SHA designs. From the tests, maximum frequency of operation attained was around 101 megahertz to 101.672 megahertz to be exact. And also performance parameters of the design were compared to the previous implementations of other hash algorithm designs. And it was found that the former have greater advantages in terms of frequency of operation compared to the latter.
This has been our presentation regarding parameterizable FPGA implementation of SHA-256 using the blockchain concept. I hope you have enjoyed it. The authors made a good job writing their paper. There has been some minor technical issues in the paper with some typos, but we managed to correct them and isolate them. But in the end, we found the paper very interesting, very informative, and we think that it has some future potential, the concept that is described in the paper. Thank you for your attention once again, and goodbye.